Welcome to Study Loop.
In this problem, we are considering the equilibrium between species A and species B. We are told that a catalyst is used which lowers the activation energy of the reaction. So here in this plot, with energy on the y-axis and reaction progress on the x-axis, the top curve here is an uncatalyzed reaction with a large activation energy, and the catalyzed reaction has a smaller activation energy. And the question asks us to use the Arrhenius equation to prove that the equilibrium constant is unchanged. All that's happening is that equilibrium is achieved faster. So let's remember the Arrhenius equation. That's some rate constant little k equals a pre-exponential factor a times e to the negative Ea for activation energy over RT, where R is the ideal gas constant and T is the temperature. Let's also remember how we are going to compute Kc. That's products over reactants at equilibrium, which I'll denote with a subscript E. So we are interested in finding whether Kc will be the same or different when we're using this catalyst. What we can do next is consider the forward reaction. So this is going to be Kf. Kf, written as the Arrhenius equation, is going to be A. I'm going to put a subscript f because that's the pre-exponential factor for the forward direction, times E to the negative Ea, f for the forward direction, divided by RT, because we're assuming constant temperature here. When we employ the use of a catalyst, the term Ea itself decreases. So that gives us a less negative exponent, and this term as a whole increases. So what happens is the rate increases. If we draw this on a plot, we can look at the formation of B over time. Uncatalyzed, there's an equilibrium concentration of B that will form. Catalyzed, that equilibrium concentration forms sooner, but it ends up being the same amount, because all we've done is speed up the rate. Let's likewise take a look at Kr. Its rate also depends on its pre-exponential factor and its activation energy. And once again, when the activation energy goes down, the rate constant goes up. And you can see that since we can't predict exactly without numbers how much Kf and Kr are going to change, simply computing the ratio Kc equals Kf over Kr is not necessarily going to work here, because we know that both Kf and Kr increase. but it turns out they're going to do so in such a way that Kc is actually constant. So we're going to instead draw another diagram. This time in the reverse reaction, we're forming A. And so we can start off and say we're trying to form some final concentration by that method, uncatalyzed. But if we take a look at blue, which is our catalyzed rate, we get to the same concentration just faster. So ultimately, with Kc equals B over A, but we can see that B and A end up being the same with the catalyst. Therefore, Kc itself is unchanged.